Hi everyone. Now in this video I am going to discuss about the pseudo force and apparent weight of a person in a lift as well as a spring balance reading. I will give that. Already I have written this content. I will show you fastly. Inertial frame of reference. First I am giving what is the inertial frame of reference. Inertial frame of reference is nothing but a frame of reference which is at rest or a frame of reference which is moving with constant velocity. We can see a frame of reference which is moving with constant velocity here, and as well as a frame of reference which is at rest. We can see this is the origin. Okay, both the frame of reference we can see they are not accelerating. Okay, zero accelerating frame of reference, also called inertial frame of reference. Now according to us, earth is at rest only. With respect to other planet, earth is moving, but according to us, earth is at rest. We can say that earth is an inertial frame of reference with respect to us. Now Newton's laws, if you want to apply the Newton's laws in this frame of reference, they are valid. We can apply happily. Non-inertial frame of reference, a frame of reference which is accelerating, nothing but acceleration is non-zero is there. Such kind of frame of reference is called non-inertial frame of reference. We can see here I have taken a frame of reference which is accelerating. Here the frame of reference is nothing but actually any moving lift, moving body, moving car, moving vehicle, anything whichever moving. No, if any observer is standing there, just to attach a coordinate system, that frame of reference is called non-inertial frame of reference. Okay, here in this Newton's second law is not valid in non-inertial frame of reference. Why this not valid in this non-inertial frame of reference, we'll see now. I have taken a lift. In this lift, there is a man is having mass m, is standing here. We can observe that, and he is standing on the weighing machine. There are the two persons who is observing the how the weighing machine reading can be there without seeing in that weighing machine. If they want to calculate by applying the Newton's law, how to get that. Before that, who will give the reading of the weighing machine? Generally, the normal contact force between the man and weighing machine gives the weighing machine reading. We can see with respect to person A I am doing now. With respect to person A, if you observe that person A, actually we can see that this person is at rest on the surface of the earth or ground. With respect to him, lift is accelerating upward direction. If lift is accelerating upward direction, if we apply the Newton's second law or Newton's laws, on mass m, normal reaction is upward direction, mg is acting downward direction, and accelerating is upward direction. So you can see as accelerating is upward direction is there, normal force is greater than the weight of the body. We can say that n minus mg is equal to ma. Finally, I am getting like a n is equal to m into g plus a. This is our true reading. If we check that reading in the whatever weighing machine is there also will get the same. If I take the example like a m is 5 kg, g is 10 meter per second square, a is equal to 2 meter per second square, then I will get the value is 60 Newton I will get. Okay, nothing but reading, true reading will be how much at 60 Newton. Now, if this person A just observe the weighing machine reading, no, he will get, it also shows that 60 Newton or 6 kilogram weight it will show. Okay, similarly person B is there now. If we also see that weighing machine reading, that also will be 60 Newton only. But if person B applies the Newton's laws on the man, okay, we can see as person B with respect to the ground, he is actually accelerating along with the lift. That's why you can see he is in a non-inertial frame of reference. Now, if we apply the Newton's second law, you can see n dash I have taken this time. Weight is acting downward direction. As man is at rest with respect to the B, man is at rest. You can observe that n dash is equal to mg. Reading we are getting like a false reading. The reason is if we apply Newton's second law, we are getting like n is equal to mg. As per our relation earlier, you will get the 50 only. 50 Newton he will get. But if you see that if we observe the machine reading, it will show like a 60 Newton. Why it is difference is happening? Reason is if we apply Newton's second law in non-inertial frame, it is not valid. How to validate this? To validate this, we need to apply an excess force. How much force you need to apply here? MA is m into g plus m into a is that MA should be added again. Some extra MA should be added. Okay, that force should be opposite to the lift acceleration. So this imaginary force is called pseudo force. If we consider this imaginary force in non-inertial frame of reference, then Newton's laws are valid. Okay, now I am discussing pseudo force. Pseudo force is nothing but it is an imaginary force applied on a body in non-inertial frame of reference. The value of this is F pseudo is equal to minus m into a bar. Minus sign indicates that this whatever pseudo force is there acting opposite to the acceleration of the frame of reference or lift here, and a is the acceleration of the lift. I have taken some examples. There is a cart, a pendulum is connected to the roof of the cart, and you can see that whenever the cart start moving, because of this pseudo force, we can observe that cart is whatever bob is there, it is moving towards the left side, and it makes some angle theta with the vertical line. At equilibrium, if I say that resolve all the forces acting on this, tension is acting. I have resolved the tension along x-axis and along y-axis. Now T sin theta is balanced by the MA, T cos theta will be equal to mg. Then I will get the angle made by the vertical line, the tan angle is equal to A by J I will get. Similarly, if I see that how this wedge is moving, suppose say a wedge is there which is moving with an acceleration A, and a block of mass m is there, then the forces acting on this body is mg acting downward direction, normal reaction acting perpendicular to the surface of the contact, and the pseudo force will be acting opposite to the wedge acceleration which is acting left side. Similarly, if I take one more case like a wedge is there, and on this wedge capital M mass is kept and small m mass is kept. If wedge is whatever capital M mass is there, if it is freely falling like with A is equal to G sin theta, now I am observing that with respect to any observer standing on the capital M mass, if you see that number of forces acting on the small m is N is upward direction, small mg is downward direction, and as acceleration of the capital M is downward direction is there, and pseudo force will be exactly opposite to that. You can see the pseudo force will be acting opposite direction. Next one, apparent weight of a person in a lift. I have taken the different situation. If a lift is actually moving with constant velocity, I have taken a person is actually standing on a weighing machine, but I have not drawn the weighing machine and as well as person, just I have written simply M only. The normal contact gives the weighing machine reading here. So you can see as lift is moving with constant velocity upward direction, you can say that body is in equilibrium. If body is in equilibrium, you can write acceleration is equal to 0. Finally, you will get upward force is downward force. In the second case also, body is moving with constant velocity, acceleration is 0, n is equal to mg. Third case, lift is at rest and normal force is equal to mg. Now we can see if lift is accelerating upward direction with A. In that case, you can see with respect to a person inside the lift, I can apply the pseudo forces downward direction opposite to the lift acceleration. I can get the mg plus ma, that is m into g plus a. N value is greater than the true weight. What is the true weight value? Mg. So whatever value you are getting weighing machine reading is greater than the true weight. Similarly, when lift is going downward direction, we can see that n plus ma, a pseudo force is acting upward direction, n is upward direction, mg is downward direction. So finally, we will get n is equal to m into g minus a, and true weight is actually normal reaction is less than the true weight. Suppose say lift is freely falling with a is equal to g. In that case, we can write it as pseudo force will be acting upward direction, that is mg only. Finally, we will get n is equal to 0 as n plus mg is equal to mg, n is equal to 0. Weightlessness condition you will get. Okay. Now, you will see that spring balance reading. If you want to measure any spring balance reading, the tension in the spring is, that tension in spring only gives the spring balance reading. In different situation, whenever problems are given, just you can observe that whatever the spring reading is there, that gives the tension in the spring is there, that gives the spring balance reading. Okay, this is about the spring balance reading. Now I am going to discuss about the constraint equations. Okay, now you observe these constraint equations. First, string constraint. String constraints. Our string constraint is length of the string is remains constant. if length of the string is remains constant, nothing but string is inextensible. If string is inextensible, I will give the one relation. You can see I have taken a string and I have connected a two bodies, A body and B body. If body B is moving with velocity Vb and body A is moving with velocity Va. Now we can see that if Va is equal to Vb, then we can say that length is constant. String length is constant. Okay, if Va is greater than Vb or Vb is greater than Va, in that case string break. If Vb is less than Va, string becomes slack or string becomes loose. Understand that? These are the situation. Now from this we can say that there is no relative motion along length of the string. Nothing but all connected bodies will have same velocity along the length of the string. All will have same velocity, same acceleration. Now I can say that if any body is like this is there, two bodies I am taking, particle 1 as well as particle 2. If particle 1 is moving with velocity 10 meter per second, if string is inextensible, we can say that whatever velocity v2 is there, no, that v2 also we can write it as how much, that v2 should be equal to 10 meter per second only, that is equal to v1. That is only constraint. Suppose say if I take the one more example, I am taking like a pulley. Let us consider this is a pulley. Here a block of first block is connected, second block also connected. Now you can see as two blocks are connected, if the first block is going upward direction with A1, that is equal to A. Nothing but each and every part on the string will move with the same acceleration upward direction, and each and every part on the string will move downward with the same acceleration this side. So you can write whatever A2 value is there, that is also A only. So from this we can write A1 is equal to much here, A2, magnitude of A1 is equal to magnitude of A2. Same diagram if I take like this, diagram I have taken like this. This is a body 2 and body 1. Now we can see that whenever this body is making an angle some theta, let us consider this is making angle theta, and it is moving with velocity v1. Now you can see I can resolve this v1 and I can say v2. Obviously if v1 is moving, first body moving left side, second body obviously will move upward direction. What is the velocity of component of this? v1 cos theta is a component of velocity along this line. You can see v1 cos theta. Each and every particle on the string will move with what velocity? v1 cos theta only along the string. As per the situation, you can write the v2 should be equal to much v1 cos theta. This is the required constraint relation between the two blocks. Okay, one more relation I will write here. We can observe that. Suppose say there is a pulley and one end of the body is connected here and other end is like this is there. Let us consider that here I have taken a body like this Okay, I have taken a body like this. It is just fitted on the a support. Okay, this body 2 is there, no? Body 2 can move only along vertical line. Vertical line. Now body 1 is there. Let us consider that body 1 is going downward direction with A1. At any instant it is making angle theta. At that instant we are going to calculate what is the A2 value. If A1 is equal to A, what is A2 value? That is the relation. We can see A1 is throughout the motion A only will be there. Throughout the string it should be A only. Now if you take A2 is like this, A2 cos theta will be like this. Now you can say that A2 cos theta along the length of the string is equal to A. Now A2 value is equal to how much? A secant theta we can write. These are the constraint relations. You can observe that how these constraint relations are there. Now suppose say if you take the any one of the body like this, I will take the two pulleys like this, and one side and other side here let us consider instead of this, let us consider a block is connected. Okay, now if this point P and point Q are there, they are moving with velocity u, and this is also pulling downward with velocity u. Now you can see at any instant if it is making angle theta, it is also making angle theta. Obviously by pulling P downward direction and Q also downward direction with velocity u, it will move upward direction with certain velocity. Let us consider V, that is moving with velocity v. Now as per the situation you can see that each string should move with the same velocity u like this. Okay, now this body is moving up velocity v. Now this component will be how much? V cos theta you can write. So from this v cos theta should be equal to u. If you want to, you can write this also, v cos theta. Everywhere it is v cos theta only, and this body q is particle q is moving with velocity u everywhere. So v cos theta is equal to u. So we can write v is equal to u secant theta you can write. This is the constraint relation for the string. Okay, now I will give the one more point, pulley constraints. Pulley constraints. If I apply pulley constraints, I will take the certain diagram. You can observe that I am taking a body. Let us consider particle 1, particle 2, particle 3 are there. Now this pulley is fixed pulley. It is a movable pulley, and we don't know which direction they are moving. Let us consider A1. Just we need to write the relation between the A1, A2, A3. I am taking A1, A2, A3. Now first give the string tensions. First string tension I have taken T. Everywhere tension T will be there. And on this body, as pulley is massless, you can see that pulley is massless. Pulley is massless. Whenever pulley is massless is there, upward tension is, let us consider the T dash. That T dash is upward direction, downward direction T, and T will be there. As T and T. Now you can see as pulley is massless, we can write T dash is equal to much 2T. You can see here 2T. Here also you can write 2T, and here also 2T. On mass M1 you can see the 2T. This is the relation. You can say that as strings are inextensible, we can write it as net work done by tension is 0. Net work done by tension is 0. What is the net work done by the tension is 0? T bar dot displacement is there, no? That x bar is equal to 0. The same, if you differentiate this, T bar dot V bar also 0. If I differentiate this, T T bar dot A bar also 0. Okay, now I am using the same relation and I am calculating this here. If I write the T bar dot A bar on the first body, you observe this carefully. On first body A1 and 2T. A1 is downward, 2T is upward direction. I am remembering this, I am writing here. On first body 2T is upward direction, A1 is downward direction. Angle between them is 180 degrees. On second body T upward direction, A2 is downward direction. Angle between them is 180. On third body you can see that T upward direction and A3 downward direction. Angle between them is 180 degrees. As per our relation, summation of T bar dot A bar value is 0, no, that I am writing. We can see T 2T into A1 cos 180 degrees plus T into A2 cos 180 degrees plus T into A3 cos 180 degrees is equal to 0. Finally, we will get the cos 180 degrees is minus 1. So, you can write 2 into A1 plus A2 plus A3 is equal to 0. This is a constraint equation. Constraint equation. By using this, you can calculate any kind of question. Okay. For example, you take one more example. Let us consider that there is a situation is there like this. Let us consider this situation is given. Whatever may the body masses, doesn't matter. I am taking first body, second body and third body. Now I don't know which direction they are moving, just I am taking this is the T, here also T, tension T, you can write, here also tension T. Everywhere, wherever contact touch is there, I am writing same tension throughout the string. Now you can see on this body 2T and downward direction also how much will be there, 2T will be there. Now what we are going to see, suppose say in question is given like this, A1 is like this, A2 is like this, A3 is like this. Now what is the constant relation? Now you can see how 2T is there. 2T is upward direction, A3 downward direction. T and A1 and T and A2. As per our relation, you can write T into A1 cos 0 degrees plus T into A2 cos 0 degrees plus T into 2T into A3 cos 180 degrees is equal to 0. So finally you can see that A1 plus A2 minus 2 A3, all T's get cancelled. So finally you will get that minus 2 A3 value is 0. This is the constraint equation. Constraint equation. Okay. Next, if I take one more example, let us consider there is a multiple pulleys are there like this. Here pulleys are there. It is connected like this. One more pulley also I am taking. One more pulley and it is connected like this, and I am taking second pulley. Now third pulley also I am taking. That's it. Let us consider body 1. Here one big body is connected. Body 2. Now if you want to write the relation between the velocities or acceleration, let us consider this body is going down with A2, other one is going up with acceleration A1. Okay, now you can see that how many strings are there. Big string is there, T I am writing, everywhere T. Now on this body you can see 2T, on this body you can say 2T. Overall we can see that the net tension on the second block is equal to 2T plus T, phi 2 is there. On the first block we can say T into A1 is there. We can see T and A1 same direction, TA1 cos 0 degrees plus Other one is 2t plus 2t plus t, 5t into cos 180 degrees, sorry, a2 also I would write now, into a2 is equal to 0. So finally we can write the a1 minus 5a2 is equal to 0. a1 is equal to much 5a2. This is my relation. Okay, next question, wedge constraints. Wedge constraints. In wedge constraints, you can observe that whenever the two wedges are given like this, I am taking one example. Let us consider there are the two wedges. One is given like this, another wedge is there. It is not starting from here, it is like this. To show the difference, I am writing like this. Okay, first body and second body. We can see that all surfaces are smooth, I have taken. As second body going with acceleration a2 right side, first body will go downward with acceleration a1, that is obvious. Now you can see what is the line here. This is like a common tangent. And I am writing one more line which is common normal. This is normal to surfaces. This is what a normal, common normal. Here our constraint is actually there should not be any relative motion. There is no relative motion along common normal, as both the blocks always maintain contact. That is our constraint actually. If both the blocks always maintain contact, we can observe that there is no relative motion along the common normal direction. I am taking both are like a particles. First particle, second particle. Okay, second particle I will write like this. Second particle is this. Now we can observe that the first particle and second particle common normal direction is this. The first particle is actually going downward direction with a1. Let us consider that this theta is inclination is there, that is theta. Now you can see here also I am trying to draw that inclination is theta. Okay, now as per our question, we can see that as a2 is right side is there, we can see that if a2 is right side is there, now a2 we can resolve into two components, a2 cos theta, and I can write the along common normal is a2 sin theta. Similarly, you can see that if this line is actually making angle theta, now you can get the a1 value is a1 into, we can write as cos theta. Along that line, we can say magnitude of a1 cos theta should be equal to magnitude of a2 sin theta. Actually, you can write the pseudo force or pseudo acceleration, you can write upward direction. That's why I have written magnitude here. a1 cos theta is equal to a2 into sin theta. Overall, we can write it as a1 is equal to a2 into tan theta. There should not be any relative acceleration along the common normal. This is my common normal. Same manner, if I take the one more example, let us consider there is a wedge, and this wedge is containing a rod. This rod is free to move along a vertical line, rod 2 and wedge 1. Let us consider that this wedge is moving right side with a1. Obviously, second body will go down with acceleration a2. We can see common tangent. This is what a common tangent, and common normal. I am writing common normal also. You can see here common normal. Now, if you apply the same relations, whatever I have written earlier, common tangent as well as common normal. See, one body is going with acceleration a1, making angle theta. This perpendicular component is a1 sine theta, and other body is going downward with acceleration a2, making angle theta with vertical line. So we can say that a2 into cos theta. From this we can write a1 sine theta should be equal to a2 into cos theta magnitude values. So we can write a2 value is equal to a1 into tan theta. As per the situation, you have to draw the diagram. This is about the wedge constraints. Wherever wedge constraints are there, we have to follow this expression. There is no relative motion along the common normal if the blocks are maintaining contact. Okay. Next one. Pulley and wedge constraints. Pulley and wedge constraints. What is the main concept behind this? I am giving that all. Okay. Pulley and wedge constraints. Here I am taking one example. You can see that already we have written that what is a pulley and what is a wedge constraints. Now you can see there is a block of mass m which is connected to the a pulley. You can see there is a pulley and it is connected to a support. Now you can see like this is it is placed on the ground theta. Now we can see if this first block wedge is moving by right side with let us consider v1. Second block, how it is moving, we are going to see. If it is going wedge is moving left side, obviously it will go down with v2. Okay, this is the relative value. Okay, now we can see that if wedge is moving x distance towards right side, we can observe that block 2 will go down the plane with same distance x. That's all. That's why if the first body is moving with velocity v1, the v2 relative value is there, no? V relative, that value also v only. Okay, that is also same. V2 value is same. So we can say that v1 is equal to v2. If v1 is equal to 5 meter per second is there, v2 also how much will be there? 5 meter per second only, downward direction it will move. Similarly, if I take the two strings are there like this, let us consider the two situations I am taking like this. There is a two situations like this. Let us consider pulley is connected like this and a pulley is connected like this, and I am taking a pulley is connected like this and a block is there. Somewhere I am taking like this also. Block is placed here. Let us consider this is the block. Whatever line I am writing now, you can see that this is a block. Okay, these are the blocks. One block is that I am writing now. So this block is there. Let us consider second block is moving with velocity v2 and the third block is there, that is moving with v3. We can see how they are moving. Here tension T will be there, here also tension T, here also tension T, here also tension T. Here you can see that 2T will be here and here tension T is there. Here also how much will be there? 2T will be there. Here also how much value will be there? 2T will be there. Here also tension T will be here. Now we can see as per the situation, the net tension is acting on the first body, second body, and net tension acting on the third body. If you see that our relation 3T into whatever V2 value is there, that should be equal to 32 into V2 cos 0 degrees. Okay, let us consider the first body is there, that I am connecting to the fixed here. It is fixed. Okay, in that case I am writing. Now you can see minus 2T plus 2T is how much here? 4T into V3 cos or plus 180 degrees. Cos 180 degrees is equal to 0. We can write it as 3v2 minus 4v3 is equal to 0. So you can write it as 3v2 is equal to 4v3. If they give any values, we can calculate by using this. Okay. Any string and pulley terms are there, we can use that. And one more thing, I am giving one more thing, like a pulley and two blocks are connected to this, body 1, body 2. Suppose say this pulley is moving with acceleration, pulley 1, movable pulley, and A1 is moving downward direction and A2 is moving downward direction. Now, as the length of the string is remains constant, as length of the string is remains constant, length of the string is remains constant, you can write it as position of the particle 1 with respect to pulley plus position of the second particle with respect to pulley is L, that is constant. I can write the velocity of the first particle with respect to pulley, second particle with respect to pulley is equal to 0. If velocities are 0, we can write acceleration of the first particle with respect to pulley, acceleration of the second particle with respect to pulley also 0. Now I write the acceleration of 1 minus acceleration of the pulley plus acceleration of the 2 minus acceleration of the pulley is equal to 0, as they are in same direction. So we can write it as a times the pulley is equal to a1 plus a2 divided by the 2. You can use this relation with vector notation. Anytime we can apply this. Okay. Anywhere if a1 is downward direction is there, we can write the downward. A2 is upward direction is there, A2 upward direction. AP is downward direction is there, we can AP is downward direction. By using this relation also we can solve the few problems. Okay. Now I will give the some other relation, like a simple questions related to this. Not the constant relations, just single pulley problems. There is a mass m1 is given and mass m2 also given. If you want to calculate the, it is Atwood machine. Atwood machine. Earlier I forgot to give this, that's why in this video I am giving. Now I am going to give that m2 is like this. Tension T and tension T. You can see that m1g is acting downward direction, m2g is acting downward direction. We can see acceleration upward direction, here also acceleration upward direction. M2 is going downward, m1 is going up, as m2 is greater than m1. Now if you want to calculate acceleration, net pulling force divided by the total mass. Total mass we can write. Net pulling force is nothing but m2g greater value minus lesser value m1g whole divided by the m1 plus m2. Overall we can write it as m2 minus m1 whole thing into g whole divided by the m1 plus m2. This is my acceleration of the pulley, acceleration of the blocks, common acceleration. Now if you want to calculate tension in the string, tension T upward direction, m1g downward direction, and acceleration of the body upward direction, we can see that upward force minus downward force, T is greater than the m1g, reason is body is going upward direction. So we can write m1 into a, substitute the a value here. So T is equal to, we can write m1g plus m1 into a value is equal to m2g minus m1g whole divided by the m1 plus m2 you can write. We can write the value T is equal to m1 square g plus m1 m2 into g plus m1 m2 into g minus m1 square g whole divided by the, you can write it as m1 plus m2. As a whole you can see that m1 square g get cancelled. Finally I will get the T is equal to 2 into m1 m2 g divided by the m1 plus m2 I can write. This is my tension in the string. Okay. Suppose if they ask like what is the tension in this support, so I can write it as T dash value is equal to 2 into T, that value is 4 m1 m2 g divided by the m1 plus m2. Now whenever the pulley system is given, the same pulley system we can replace like this. A string is connected to a new mass, that mass can be written as 4 m1 m2 g divided by the m1 plus m2. Like this we can write. This is T dash. Understand that? that we can replace with sorry, G is not there. Okay, now you can see that 4 m1 m2 by m1 plus m2 you can replace if you want to do any questions. Okay, now one more last thing I will give, and let us consider that there is a system is given like this. First body and second body. Let us consider tension in this first case is equal to T and the second also T. And what is the net force acting on the pulley? Net force acting on the pulley, as they are in perpendicular to each other, we can write F is equal to under root of T square plus T square, that can be written as root 2 into T. Suppose say these two are inclined at certain angle theta. If T and T are inclined at a certain angle theta, then you can write T square plus 2T square into cos theta. By using this, we can write it as a net force acting on the clamp. Okay, force acting on the clamp. Acting on the clamp. So these are the points we can observe while doing problems. These basic concepts we can apply for the solving problems. Okay, this is about the basic information related to the laws of motion. We can refer that all the questions. Okay, I have done the questions also, but it is too much lengthy videos are coming. That's why I am not showing that relations and all. You can practice JEE mains, previous JEE mains questions are there, no, that you can practice. Okay, if any doubts are there, you can ask. I will post that questions. Thank you very much. We will continue in the next lecture with the next video with the friction. Thank you very much.